So last time, I begin now. Last time we discussed the Stokes formula. Do you still remember what it is? So the statement which I made, I'm going to prove now, is that if you have an n-dimensional manifold with boundary M and dm, M is compact, hence dm is also compact. M is oriented, and hence the M is also oriented. This is important. Not just oriented, but orientation has been fixed. Then for every form of degree n minus 1, so we have M. The dimension is n, and alpha is a form of degree n minus 1 on M. Oh, yes. Thank you. Degree n minus 1 on M. And then the two naturally arising integrals. The integral of alpha over dm and the integral of d alpha over m are equal to each other. This is the Stokes formula. And last time I said something about this formula, about many other formulas which are implied by it, formulas from standard multivariable calculus. And also there are many other results which follow from this. We'll be able in my last lecture to discuss some of them. Also I said something about the name, which I hoped I expressed my great respect to Stokes, but certainly this formula does not belong to him, either in this form, in which he even wasn't able to formulate it, or in the form which is usually attributed to him. Also, actually, he was not the first to discover it. Now, I said that with all great importance of this formula, the proof is sort of unfairly simple, short. I can make it look longer and more complicated, but you will see that actually nothing. So first of all, this equality, the left-hand side and right-hand side both are linear with respect to alpha. So if alpha is the sum of other forms of degree n minus 1, then it's sufficient to prove it for every summand. Then it will be true for the sum. With this in mind, we can do what we always do with such things using the partition of unity. I did this last time simply when I defined the integral. The fact is that we can assume that alpha that the support of alpha, that is the closure of the set where it is not equal to 0, the support is contained in one chart, after which this statement becomes actually a statement about forms in Euclidean spaces. Now, a chart. Again, I can suppose this chart, you remember there is such a thing as Rn minus. For my purposes now, it is convenient to consider this as the set where x1 is non-positive. There are various possibilities for that. And then the boundary of this is the set where x1 is 0. And actually, I also suppose that the domain of the chart which should be an open set in this is contained in the cube. Every coordinate is between -1 and 0. Such strange cube, but I consider this precisely. It is open. So actually, the faces of this cube should be disjoint from U with one exception. You understand? This is my space R and minus. This is my cube, and U may be like this. The domain may be like this. So it can touch only this face. All the other faces certainly are disjoint from U simply because U is open in R and minus. Is okay? Then the form. So at this moment I can forget about M. And my form is an n-1 form in this in the space R n minus, which is with the support is containing in U, in this cube. Now next thing, my form alpha. It is the sum of monomials, and since my equality is linear, I can assume that this is just one monomial. This one monomial is f, function of all x's, times all the differentials of the coordinates with one coordinate immediate. This is alpha. Then d alpha. It's plus minus actually -1 to the power I minus 1. Or I can write just f df over dxi this thing. This is the differential, right? Because all the other differentials are here. I may be anything from 1 to n. Now next thing. I consider the two integrals. The integral over R and minus 1 n minus, yes, of this form, df dxi dxi and so on, is the same df or dxi dxi with many other integrals, all from, excuse me, this is very much wrong, from -1 to 0. Now this integral is well known to us. It is f taken for xi to be 0 minus f taken for xi -1, right? And if I is not 1, then both are zeros, right? So if I is not 1, then this integral if I is 1, then of this, so I is 1, then this is not necessarily 0. This is again 0. If I is 1, then it is the integral f with x1 taken to 0 dx2 dxn, which is precisely, whether you want it or not, precisely the integral over d Rn minus d alpha, which completes the proof of the Stokes formula. So actually, and you may be familiar, especially if you teach it, you may be familiar with the proof of different particular cases of the Stokes formula, like the Green theorem, many other theorems like this. And actually, the proof uses only the fact which you call the fundamental theorem of calculus, and in European textbook usually called the Newton-Leibniz theorem. So this also is a particular case, as I explained last time, of the Stokes formula, but it is the only case when you need some proof. Since we have this proof, I don't consider it here. But the whole lot of these formulas follow immediately from this theorem number 1001 in the calculus, which relates derivatives to integrals. Yes?
Do we have anything like Stokes formula in the infinite-dimensional manifold, or
Infinite dimensional? Very interesting question. You see, actual theory of infinite dimensional manifolds, we do not consider it here, is not so well established because, first of all, it is not very much clear what an infinite dimensional manifold is. Finite dimensional is based on n-dimensional vector spaces, and it is known what it is. Infinite dimensional spaces, there are many other infinite dimensional spaces. There is a book by Lang. Lang wrote, if you search Lang, wrote dozens of books, and one of them is called Differential Topology. Remember lectures, something. So differential topology of manifolds is a part of the title. I am not a big fan of this book, but Lang certainly considers the infinite dimensional case. It is definitely so. Now, this is a manifold. Now, integrands. If the integrand is a form of finite degree, then actually you do not know anything. You do not need anything regarding the ambient manifold. It is all the same. But there are theories which involve forms of infinite degree, and then the integral becomes something feasible. I definitely will not go into details here. This theory is sort of complicated, not well established, but still it exists if you want to know this, Patrick. More questions? Other questions regarding this, or this seems too trivial to you to ask questions? Now, having this fact, I want to show to you immediately two of the most immediate consequences of the theorem. You remember that there are closed forms and exact forms. Now, suppose that in some manifold, or I don't know what dimension, even infinite, we have an exact form. So alpha is in alpha n of well, W. W is a manifold of dimension maybe more than n. Now M, n-dimensional submanifold. An n-dimensional submanifold. And without boundary. Compact and dimensional compact, everything is compact and oriented, and if I at some moment forget to say this, I didn't hear any of this. Then I want to say, no, you want to say, what do you think of the integral of alpha over m? Do you have an opinion about this? 0. 0. Nothing can be more clear than this. It is 0. Why? This is because if alpha is d beta, which precisely means that the form is exact, then this by the Stokes theorem is this, but this is empty. So this is 0. This fact, again, it is very obvious, very I don't know what. But the proof is obvious. So the integral of an exact form over any manifold without boundary is 0. Now, what if the form is not exact, but rather closed? You remember, there are exact forms, which are differentials. There are closed forms, forms whose differential is 0. Every exact form is closed, but it is not true that every closed form is exact. So now we are looking for a generalization of this fact. Is it possible to expect that the integral of a closed form over m is necessarily 0? What's your opinion about that? You don't want to express an opinion, but the right thing is as usual. It is sort of true and sort of false. It is false because it is false. There are counterexamples. It is very simple. It is true because it is true under a very natural additional condition. Under a very natural additional condition. Can you imagine what condition should be? What the condition should be? M, as I say, is an n-dimensional submanifold without boundary, but to conclude that the integral of every closed form with respect to over m is 0, we need to know more about m. Compact, yes, it is maybe not written there, but I said this. M is compact and orientable. This is an oriented. This is, well, for 0 it is orientable. It is already so. We don't need to assume this. But we need to assume something. Yes, Doug?
Trying to make it something corresponding to having a conservative field.
Let me say that the answer consists in 2 or 3 words. You don't need to say simply M itself should be a boundary of some submanifold of W. So actually, if imagine that W also contains some n+1 dimensional manifold with boundary. And the boundary is M. Oh, dn. And alpha is closed. which means that the alpha is 0. Then the integral of alpha over m, that is the integral of alpha over dn, is the integral of over n d alpha, and it is 0 because the alpha is 0. For example, if you have, say, a smooth, closed, non-self-intersecting curve in the plane, understand? Then it bounds some two-dimensional manifold with boundary, which means, so this is my example. W is the plane, this blackboard, and M is this. Then M bounds some n, and by this reason, the integral of any closed form is 0. The form should be defined in the whole W, or at least in some neighborhood of this n. If, however, W is, say, the open annulus, and this is a submanifold of dimension 1, right? This is submanifold dimension 1, and then it is a submanifold. We can consider integrals of forms of degree 1. The integral of an exact form of degree 1 is 0 because we have the theorem. But this submanifold of W is not the boundary of some two-dimensional submanifold with boundary because of this hole. And actually, it is very easy to find an example of a differential form within in W, which is closed, not actually exact, and the integral over this submanifold is not 0. Moreover, if the integral is not 0, then we know definitely the form is not exact. So actually, we have now in our hands some instrument to distinguish between exact forms and closed forms. We have a closed form, and we want to know whether it is exact. We definitely know a possible obstruction to this. If we have a closed form, and there is a submanifold of the dimension equal to the degree of this form, submanifold without boundary, you understand? So that the integral of this form over this submanifold is not 0, then the form, let it be closed as much as you wish, cannot be exact, because exact forms have 0 integrals. And if we construct a form on this annulus, closed form, say that its integral over this closed curve is not 0, then we know definitely that this form cannot be exact. Do you understand? More can be said about this, but I want now to formulate sort of a result. And you will say to me how much plausible it seems to you. I really don't know what you will say. Suppose that we have a closed form on some manifold. And suppose that we know its closed form, its integral over every form of degree n. Manifold has dimension more than n. form degree n, and its integral, we know that, suppose. Integral of this form over any, absolutely, n-dimensional submanifold of this manifold with boundary is 0. Do you think it is sufficient to be sure that the form is exact? So if any integral of this kind is not 0, form is not exact, forget about it. But if all the integrals are 0, do you think it's plausible that the form will be exact? Why do you think so, Henry?
Not certain, just intuition, but no good reason.
You are right, actually, but it is sort of deep. Sort of deep. Actually, again, this statement can be made correct. Simply, it is not sufficient to consider submanifolds. In the language which is familiar to you, Henry, I can say that we can take integrals over cycles of dimension n, and if all of them are 0, then the form is exact. That's okay. If you want to stay within the realm of manifolds, you should consider manifolds with some mild but still some singularities. Then they will be correct. Certainly, for a manifold like an annulus, it is correct. In higher dimensions, it is possible that actually a manifold simply does not have sufficiently many submanifolds. And by this reason, it may be not true. But something like this should be true. Now the next, so this is all in some sense. We stop here because I want now to discuss a different thing. So if you have questions regarding this, you, Dale. No. You, Virgil. If you have questions regarding this, then it is the best time to ask. You have good questions usually, Patrick. No? Well. Other people, so nobody wants to ask anything. What I want to say now actually is closer to classical topology. You remember that first of all, we have such a thing as de Rham cohomology. De Rham cohomology of degree q, the definition is very superficial. We just consider the space of all closed forms on a manifold. It's subspace consisting of all exact forms on this manifold. When we have a space in a subspace, we have a temptation to form the quotient. It happens that if your manifold is compact, then actually this quotient between two very much infinite dimensional spaces is finite dimensional. This is a separate result. And what I want to say now, simply that this quotient is called qth de Rham cohomology of M. So HQ de Rham of M is this quotient. Closed Q forms over exact Q forms. Actually, for those of you who have any knowledge of algebraic topology, for example, knowledge that this subject exists, I can say that there is a theorem which is usually called de Rham theorem, which states precisely that this cohomology is the same as any other cohomology. Cohomology of M has, which is considered in topology with the coefficient in real numbers, because we consider real forms. So this, from the topological point of view, this subscript dr is not necessary, it's simply cohomology. The Rham theorem. Question?
Yes.
Yes.
So is there any way to associate a homology theory with this as well, or you only have cohomology?
You see, since since we have real coefficients in a field, homology is, if everything's fine, it's simply dual space. But actually there exists a way how to describe homology geometrically, and it will not be anything related to differential forms. Actually, singular homology, say with smooth singular symbol, made out of smooth singular symbolicity, is the homology theory, which is very much related to this by through the integration. But I understand the question. Now I want to say that there are some properties which are expected in topology and which hold here. Also, I want to say, maybe it's necessary to say, if some of you is interested, there are many proofs of the theorem, the RAM theorem, which I was not able even to formulate properly here because I don't have the topological notions. And maybe the most popular proof comes from the so-called sheaf theory. I will not discuss it now, but I will discuss it together with many other subjects in my course of homological algebra, which I'm going to teach this spring. So I will prove the RAM theory. Now, if we have two manifolds and a very much smooth map between these manifolds, then there arises, and we discussed it several times, for every Q, the map between differential forms in the opposite direction. This map commutes with the differential, which means that it takes closed forms into closed forms, and exact forms into exact forms. So there is a map of this into this, this into this, and hence a map between the quotients. So there arises a map also denoted as F upper star between these homologies, quotient into quotient. That's all. Is clear, Patrick? If we have a map of linear map of a vector space into vector space, which takes a subspace into subspace, then also it induces a map between quotients. Nothing can be easier, right? It is certainly bad that we have the same notation for differential forms in common, but I will rather consider this. In topology, there exists a notion of homotopy, one of the most fundamental notions of algebraic topology. What does it mean? Have you ever heard? Well, some of you definitely heard, but I asked people who didn't participate in my topology classes last year. So, Patrick, are you familiar with this notion? Two maps are homotopic. Dale. Two maps are homotopic. Doug. Homotopy is simply deformation of one map into another map. So we have a map, and then we deform it continuously, and we get a new map. These two maps are called homotopic. In our differential setting, I define it slightly differently, but actually in an equivalent way. F and G are homotopic. So we have F and G, two maps of M and N. If there exists a map If you prefer, you can write 0, 1 here. Into n, such that f restricted to m f and f restricted to m cross 1 is G. So such a map of a cylinder which joins these two maps and intermediate sections give you a deformation, homotopy of this into this. So this is called a homotopy. Questions about this? Maps may be homotopic or not. Say, if you have a map of a circle, any two maps of a circle into the plane, it's very easy to prove that they are homotopic always. But say, let me give you an example of maps which are not homotopic. Say n is the annulus. M is a circle. Two maps are this. This is F, and this is G. I draw rather the image of the map, but you can imagine how the map looks like. So a circle is mapped into this annulus. In one case, the curve goes around the hole. In the other case, it doesn't go around the hole. These two maps are not homotopic. Easy to believe, not so easy to prove, but it is fact. It is true. Not so easy to prove, mostly because it's always difficult to prove theorems which seem immediately obvious geometrically. What to prove? Certainly, just look at it. So to map may be homotopic or not. And now I want to say that if two maps are homotopic, then the induced maps in the de Rham cohomology are the same. If you want to express it in a less clear but shorter language, you can say that de Rham cohomology is homotopy invariant. Certainly I will prove this, but just to be on the safe side, I want to begin with some simple corollary of this. A proof again is short, just some computation. F homotopic to G, so we also have this capital F to produce the proof. For example, let me take two manifolds. You may think that I will consider something complicated. No. By the way, in differential topology, everything is not complicated. All the counterexamples, everything. Actually, very simple constructions. But in this case, this is aggressively simple. I consider Rn and 1 point. There are two maps, F of Rn into 1 point and 1 point into Rn. This is, there is only one map in the 1 point space. Here, for example, this goes to the origin, or any other point which you like more. Now, so this is F, this is G. I will apply homotopy inverse not to these maps. I now consider the composition of these two maps. Rn is collapsed into 1 point, and this point then is mapped here. This map certainly is constant, sort of not very interesting, but it is homotopic to the identity. Imagine a map of the whole Rn into 1 point is this Rn. You can make a homotopy of the identity, which relates this map with this map into one point, right? You understand, Patrick? A map of the whole Rn into one point, you can such a radial homotopy. So the first map, identity, takes any point into itself. This is 0, and then during my homotopy, this point goes along the straight interval, and after the homotopy, the map G, the map to which it is homotopic, will be just map into one point. So these two maps are homotopic. Since, this is the identity. This means, according to this result, that they induce the same map in cohomology, right? Consider HQ theorem of Rn, and suppose that Q is positive, not 0. This map, we first and then this, right? So this composition, but what do you think of this space? Just one point. I personally have never seen any non-zero differential form of a positive degree on the one-point manifolds. Maybe you were more lucky. So from my point of view, this is 0. And hence, the composition is 0. On the other hand, it is the same as this. But identity is identity. Identity will be also identity on all differential forms, closed form, exact forms, and cohomology. So for this strange space, HQ theorem of Rn, the 0 map is the same as the identity. How could it be? I personally see only one possibility for that. Maybe you see more. If the space is 0, then the 0 map with identity are the same. If the space is not 0, whatever, but not 0, then the identity map is not 0. Takes some vector into non-zero vector. So from this, it follows then that HQ theorem Rn is 0 for Q greater than 0. What does it mean? HQ theorem is 0. HQ is the quotient of closed forms over exact forms. How it is possible that the quotient is 0 between two spaces? Again, it's possible only in one case, when you factorize the space over itself, right? If you factorize the space over anything which is not the space, some smaller, the quotient will not be 0. So this means that for Rn, the notions of closed forms and exact forms coincide. Well, it is always true that an exact form is closed. But for Rn, we know now that also a closed form is exact. This is a very classical result, actually preceding all this theory which we consider here. And it's called the, such names is better to remember. It's called the Poincare lemma. The Poincare lemma says that if you have a closed form of positive degree in the green space Rn, then it is a differential of some form of degree n minus 1. It's true for every positive Q. right? Well, my friends, I wanted to prove the homotopy theorem, and I had this actual idea that maybe it will not be possible, because I have 3 minutes in which I want to say only that the proof is very short. Now, just not to waste these minutes, which we value a lot, I want to, next time, my last lecture, we will discuss the RAM cohomology not only for Rn. I will say something. I will say something. And the first thing which we will prove here is that the RAM, I will be able to prove this, the RAM cohomology of a sphere. A sphere, Sn, n-dimensional sphere. The Poincare lemma almost holds for it. If we have a form on this differential form on the sphere, which is closed, then it is exact. If its degree is positive, precisely as in the case of Rn, but also less than n. Between 0 and n, if q is 1, 2, 3, n minus 1, closed forms and exact forms are the same. And if the degree is n, then you know only too well that it cannot be the same. Because if we have a closed form of degree n on Sn, my friends, to be exact, it should have zero integral over the sphere. And why should it have it? Every form is closed. Dimension degree n on Sn. And the interval may be not zero. If it's not zero, then it is not exact, cannot be exact. The fact which requires some proof that if the interval is zero, then it is exact. So we will discuss next time some theorems like this. And now let us, so this is all.